I'm going to break one more assumption that we made. We said that the rise and fall delays are equally important, and therefore both of them had to be equal, right? We said both pull-up resistance and pull-down resistance had to be R. This is not always true. For example, when I'm dealing with a memory, I might want to turn on the word line of the SRAM cell very quickly, but it's okay to turn it off slightly slowly, right? Therefore, the rising edge is more critical than the falling edge. Okay, which means now there is an opportunity for me to reduce the logical effort on that particular edge. Till now, we have said the logical effort of an input A, B, C. We have found out logical effort. We were very clear that the logical effort depends on the input. Now it's not only dependent on the input, it's also going to depend on the rise or fall. Okay, and this leads us to the concept of a skewed gate. Okay, so let me now draw the symmetric static CMOS gate 1, 2. Now let us say I want to favor the rising edge, or no, let me take the other case first. Let's just say I want to favor the falling edge. I want to favor the falling edge, and therefore I am going to call that a low skew inverter. Right? So what I'm going to do is I'm going to do the following. I now need to size this accordingly. Okay, so I will not put the size down right now. So what I want to ask you is, if I want to favor the falling edge, right, and I want to reduce the logical effort, what should I do? Increase the size. Okay, so you're saying instead of 1 and 2, you want me to make this, let's say, 2. But if I make it 2, what's going to happen to the logical effort? It will increase, because remember, logical effort is, it doesn't depend on whether it's 1 or 2, because I'm going to compare it now to a reference static CMOS inverter with the same drive strength. So if you give me a NMOS with size 2, I will construct my reference inverter which also has an NMOS of size 2. Right? So the key point here, and that's what I pointed out in the asymmetric gates, is it may be counterintuitive that I am increasing the resistance of that transistor, but my main aim is to reduce the capacitance. Okay, so therefore this is really not possible. Now again, what is the logical effort? It is basically C NMOS plus C PMOS by 3C. Of course, if it's a symmetric inverter, then it's going to be the same. It's going to be 1. Now, I want to improve the logical effort on the falling edge. The falling edge, right, is determined by the pull down stack, and therefore it is determined by the NMOS transistors, capacitance, resistance, and all that. This guy is just a dead weight that is adding to the capacitance if I consider only the falling edge. When I'm falling, when the output is falling, there is a capacitance that's coming from the PMOS transistor, but the PMOS transistor is not adding anything or not reducing the delay of my falling transition at all. Therefore, should I increase the capacitance of the PMOS transistor or should I decrease the capacitance of the PMOS transistor? I have to decrease the capacitance, and therefore this 2 I will make 1 and I will keep this as 1. Here what I have done is, since the falling edge is important, I am not changing that resistance. That is already R. I cannot increase that resistance now, right, by making that smaller. So the other option is, of course, if I make this as, let's say, half, you might think that the capacitance will drop, but then my resistance is increasing. You can only do this resistance increasing if another transistor on the stack is able to compensate for that. Clear? Therefore, I cannot make this half. I need to keep it as 1. But the top guy, PMOS transistor, I can make it as 1. Okay? Now, with this kind of a sizing, I am now going to go ahead and find out the logical effort for each of the edges, rising edge and falling edge. Okay? So, let me take this guy. One. Okay, and I'm going to look at logical effort of pull down. Okay, this is equal to pull down logical effort. I now need to compare the capacitance offered by this gate to the capacitance of a symmetric static CMOS inverter with the same pull down strength. Because now I am talking of the pull down case. I am talking of the falling edge. Therefore, I am now going to construct my reference CMOS inverter. Okay, this is my low skew inverter. This is my reference static CMOS inverter. Okay, you have to tell me what these sizes should be of the NMOS and PMOS transistors. I have to compare the capacitance of this low skew inverter. Okay, what is the capacitance, by the way? CA is 2C to the capacitance of a symmetric static CMOS inverter with the same pull down strength. Earlier I just said same drive strength because pull up and pull down were the same. Now I am going to add an extra rider and say with the same pull down strength. Therefore, this transistor size should be maintained the same, 1. Right? Clear? Now, if this is 1 and I want this reference inverter to be symmetric static CMOS inverter, what should the PMOS be? Exactly. Therefore, the capacitance here, CA, I'll call it CA prime, is 3C. Therefore, the logical effort, GA, is going to be what? 2 by V. What was the logical effort of a reference static CMOS inverter? 1. I have brought that down to less than 1. What's your intuition about what will happen to the logical effort on the rising edge? Yeah? It has to increase because that's how I have brought this guy down by sacrificing that edge. I have, I've been mucking around with the PMOS transistor and therefore I have to pay a penalty there. Therefore, we will now go ahead and calculate the logical effort of the pull up effort. Okay. So here is my low skew inverter. This is 1, and I said this also is 1. Okay. I am now going to compare this with a symmetric static CMOS inverter with the same pull-up drive strength, because I am now looking at the pull-up logical effort, which implies that this one should be the same here. Okay, this is my reference static CMOS inverter that I am going to compare against. Right? Reference symmetric static CMOS inverter. If the PMOS is 1 and I want this to be a reference symmetric static CMOS inverter, what should be the NMOS? Half. Only then that pull up, pull down strength will be the same, and therefore this will be half. So the way is this gives rise to this 1 here, then this will tell you how much this should. Right? In the previous case, because I was looking at pull down, I first calculated this, then this told me that PMOS should be 2. So get that direction right. You have to fix one transistor and then get the other one according to the symmetric constraint that we have. Okay. Now if this is 1, so what is the capacitance? CA is how much? This is still 2C. What's the capacitance here? CA prime. 3 by 2 C. Therefore, G pull down is how much? 2, it's basically 2 by 3 by 2. 4 by 3. Oh, sorry. Pull up. Clear? So what did we do? This clearly is greater than 1. For a low skew inverter where I am favoring the falling edge, I brought the logical effort to 2 by 3. But I had to increase the logical effort for the pull up to 4 by 3 in the process. Clear? So similarly, you can construct what is known as a high skew inverter. Okay? High inverter. So this is my reference static CMOS inverter. I want to construct a high skew inverter, which means I want to favor the rising edge. Rising edge is determined by the PMOS. Therefore, the PMOS I want to leave it as it is, because that resistance is already R. I can't reduce that any further. Therefore, my high skew inverter will be like this. This is fixed. So when the output is rising through the PMOS transistor, the capacitance that is coming from the NMOS is a dead weight. Therefore, I am going to reduce that capacitance. So I will make this half, assuming that the unit width is larger than the minimum width allowed in the technology. Okay. So what I mean is, this 1 is going to correspond to some, let's say, 8 lambda by 2 lambda, and this is 16 lambda by 2 lambda. And let's say the minimum width allowed in the technology is 4 lambda. Then this half is still allowed. That's what I meant. Doesn't mean that half cannot be used. It just depends on the absolute minimum width. Remember, these are relative sizings that I've been speaking about. Therefore, this half is allowed. Right? So now I am going to calculate the, so before we start, logical effort of pull up and pull down. Which one will be greater than 1? Which one will be less than 1? Pull down will be greater than 1. Pull up should be less than 1. Right? That's the aim. So what's the capacitance of this? Yeah. What? 5 by 2C. Okay. Now I am going to calculate logical effort of pull up, logical effort of pull down. Okay. This is my reference static symmetric inverter. I'm going to construct these two things. So I am now looking at pull up. I have to compare this high skew inverter that I have to a reference static CMOS symmetric inverter with the same pull up strength. Therefore, this 2 here has to appear on the PMOS. Now, if that is true, what should be my NMOS for this inverter to be a symmetric static CMOS inverter? 1. Therefore, this will give me 1 here. And therefore, the capacitance Ca prime will be how much? 3C. And implies the GPU is how much? Yeah? 5 by 6. Obviously, this is less than 1. Now, I want to calculate the logical effort of the pull down. What should I do? I have to compare it with a reference static CMOS inverter with the same pull down strength. Therefore, this half has to appear here. If this is half, what should be the PMOS? 1. Therefore, Ca prime is how much? 3 by 2 C, which implies GPD is how much? 5 by is greater than 1. Clear? Any questions? Yeah. So again, that will, like I told you, it depends on the minimum width in the technology, right? Then it also depends on the layout asymmetry and all that. So the numbers that have been suggested in the textbook are typical numbers that are sort of usable practically. That's all. But the idea is not, of course, I don't want you to get stuck with these numbers. Even if I make it 1 by 3, you should be able to calculate the new logical effort, right? It's not tied to this. There's nothing, there's no unique solution for these numbers here. It's driven by practical constraints and some usable numbers, and sometimes it's just a heuristic. That's all. Any questions? So now you can take this idea of a high skew inverter and take it to a NAND gate, take it to a NOR gate, and so on. Right? So for example, if I have 2.5, right? I want to now construct a high skew NAND. What am I going to do? Right? A, B, and A and B. So what will be my sizes of these transistors? I want it to be a high skew NAND. So the PMOS should be 2, right? You don't change that. This will be 2. What should be the NMOS sizes? The net resistance should be how much? R? No. What is this net resistance here? The blue. This is how much? 2R, right? Whereas this top resistance is R. Because that is R, I said you need, let me just color code it so that it's easy to follow. This should be 2 and 2. But bottom, the net resistance should be 2R. Therefore, each transistor should be R, and which means that the size should be 1, 1. What about a high skew NOR? What should be the size of my PMOS? 4, 4. Because the net resistance should still be R. It's a high skew NOR, and therefore this size will be 4, 4. What about the NMOS? Half and half. Right? You can now go ahead and calculate logical effort for these gates also. The NORs and NANDs also you can calculate. I will leave this as an exercise for you. Please, you can refer my slides here. So what is shown here is basically the unskewed gate. Pull up logical effort is 1, pull down logical effort is 1. NAND 2, pull up logical effort is 4 by 3, pull down is 4 by 3. NOR 2, 5 by 3, 5 by 3. Right? The top row is an unskewed gate. High skew inverter, we saw the logical effort is 5 by 6 and 5 by 3. Right? 5 by 6 for pull up, 5 by 3 for pull down. The NAND gate, logical effort pull up is 1 and 2. Now remember, it's not that this should be above 1 and below 1. You have to compare this 1 and 2 with respect to 4 by 3. The pull-up logical effort has become 1 as opposed to 4 by 3. The pull-down logical effort has become 2 as opposed to 4 by 3. So 4 by 3, 1 has become 1, other has become 2. Similarly here, with regard to 5 by 3, the pull-up logical effort has become 3 by 2. Right? 1.67 and 1.5. Whereas the pull-down logical effort has become 3. Okay? So low skew again. The inverter we saw is 4 by 3, 2 by 3. The pull-up logical effort now has become 2, pull-down logical effort has become 1. Okay, this is a low skew inverter, remember, therefore the sizes are 2, 2, 1, 1. The PMOS has been compromised. Clear? Similarly, for a NOR, the pull-up logical effort again is 2, pull-down logical effort is 1. So please go and work these out on your own. Okay, it's this, you have to do the same thing, you have to construct the symmetric static CMOS inverter. That's the only step that you have to get correct. Once you do that, it's just a question of dividing by the capacitance. Clear? Okay.